So today we're just going to do like a really brief intro to chemical reactions. So just some foundations. So like what are chemical reactions? And then really we're just going to build the groundwork of how do we write chemical equations. So first to start, let's talk about all the chemical reactions that happen in our everyday lives. So there are lots of chemical reactions that happen both inside your body and just around you all day, every day. Okay. So take a minute, chat with the people at your table, and how many of these reactions can you identify? So what reactions can you identify that happen in your body and around you, outside of the chemistry room? Okay. So your car battery is a chemical reaction. How many of you have rust on your car?
No, I have rust on my skateboard.
Okay, rust. So rust happens around you.
I've noticed that lately. I've left my silverware in the dishwasher for too long and it starts to rust. I'm like, oh.
Oops.
And so now I have to
We have cooking food. What about photosynthesis? Is that happening around you all the time? Okay. So the point of this was to point out chemical reactions happen all around you all the time. You don't just have to be in chemistry class to think chemical reactions are important. Okay, so they happen all the time in your body, around your body. Do we need chemical reactions? Yes. So then let's start with what do chemical reactions look like and what happens? So during a chemical reaction, one or more substances that we call reactants are going to change into one or more new substances that we call products. And when we write chemical reactions down, we put reactants on the left side of the equation. Then we use this little arrow. That little arrow just means yields or produces. So it's what are you making? And then we put products to the right side. And it's always, always, always reactants on the left, products on the right. So make sure you definitely get down kind of our generic outline of what a chemical reaction would look like. Okay, so let's look at how chemical reactions actually work. Okay, so the bonds that hold those reactants together are broken, and then those atoms just rearrange to make a new product, and then new bonds are formed. So a really big key idea is during chemical reactions, atoms themselves are neither created nor destroyed. They're just rearranged. Okay, and that goes with the law of conservation of mass, or sometimes you'll see it as matter. Okay, so during chemical reactions, you can't just have new atoms poof out of thin air, nor can you have them disappear. So what happens is you have the same atoms, they just rearrange to make something new. So take a look at my example down here. This is zinc plus hydrochloric acid. This is the same reaction we did, I think, last Monday, right?
Yes.
Okay, so exactly a week ago. So you started with zinc, and we added it to hydrochloric acid. Zinc, what did zinc look like before you actually reacted it? What color was it? Silvery, right? It's just these small little grainy silvery chunks of metal. Okay. And then when you added it to the hydrochloric acid, what happened?
It crystallized.
Okay, it bubbled first, right? It bubbled, and that made some hydrogen gas. Okay, and then eventually it crystallized, and that was the zinc chloride. So notice in this reaction, the three elements we start with is zinc, hydrogen, and chlorine. Notice you still have those exact same elements in the product, right? You still have hydrogen, we still have zinc, we still have chlorine. But notice it just got rearranged, okay? So I think a big misconception for people is during a chemical reaction, you're going to make something new. Well, you make something new in the sense you made hydrogen gas and zinc chloride, but notice you didn't get a new element. We just didn't get calcium in here, right? So you can only have the same elements that you start with. And then law of conservation of mass, you can't just have mass either randomly appear out of thin air or disappear. So let's say you started with 5 grams of reactants on this side of the reaction. How many grams would you have on the other side? The same amount, okay? So you can't just have mass just like poof and disappear or magically appear. Okay, so one way we can talk about chemical reactions is word equations. This one I didn't bold, so you don't have to write the word equations down. But word equations are exactly how they sound. So all we're doing is using words to describe a chemical reaction. So an example for rust would be iron plus oxygen yields iron 3 oxide. Another example, hydrogen peroxide breaks down into water and oxygen. Or maybe a combustion reaction, methane plus oxygen gives us carbon dioxide and water. Okay. So we can always use words to describe reactions. However, is it easier to write hydrogen peroxide or H2O2? Okay, H2O2. So when we write chemical reactions, we'll use the formulas. Okay. So then we're going to learn just kind of the foundation of writing chemical equations today. We'll build on this on Wednesday. Okay. So when we write chemical equations, we're going to use formulas instead of words. So instead of hydrogen peroxide, we'd write H2O2. Okay. And then the first step is to write something called a skeleton equation. What do you think of when you hear the word skeleton? Just like the bones, like the bare bones minimum, right? So your skeleton equation is just that. It's like the bare bones minimum. So all it's going to show are the actual chemical formulas in your reaction, like your reactants and products. It is not going to be balanced at this point. Okay. Our next step is when we write our chemical equations, we do indicate the physical state of the substances. How we do that is we just use these little symbols, and these look like subscripts. Okay, so you put a little s in parentheses to communicate something will be a solid. Okay. An L is for liquid, a G is for gas, and then put down aqueous, because this is probably the new one for you. So AQ means aqueous, which just means the solution's dissolved in water. Okay, so think Kool-Aid. How many of you have made Kool-Aid? Right, you dissolve the Kool-Aid powder. Kool-Aid is an aqueous solution, right? So the Kool-Aid powder itself, you didn't actually melt it and turn it to a liquid, so it's not a liquid. Instead, it dissolved in that water, so that's what aqueous means. And then here's an example of how that would look. So if we had solid iron, we'd write Fe, and then this little S down here, that's how we communicate it with solid. Okay. Then it reacts with oxygen. In what state, like physical state, is this oxygen in? Okay, gas. That little G tells you gas. And then it makes iron 3 oxide. And again, what state, like physical state, is this product? Solid. Okay. So this is the reaction for rust. So we always put the physical state, and that communicates, are we working with solids, liquids, gases, or aqueous solutions? And then finally, a lot of reactions take a really long time to react. Okay. And we don't necessarily have that much time. So sometimes catalysts are used. Okay. If you don't remember a catalyst from bio, you can write catalysts just speed up reactions. Okay. And they speed them up without being used up, which means catalysts, they're not a reactant, nor are they a product. They're just kind of there. Okay. So then the way we communicate if a catalyst was used, we write it above the arrow. So it can't go on the reactant side because it's not a reactant. It can't go on the product side because it's not a product. So we just write it above the arrow. Okay. So here's our example, hydrogen peroxide. It breaks down into water and oxygen gas. This happens slow. Like this is a really slow process. So if we want to speed it up, we just add some manganese dioxide. So we write it above the arrow. Down below, I just have some other examples. Sometimes you have a reaction that you have to carry out at a specific temperature. If you know that specific temperature, you can just write it above the arrow. The most popular one for us is the second one. Okay. Sometimes you just use like general heat, right? We just want to speed it up and use heat. This is what we did last week with the zinc chloride, right? We needed that water to boil off. But whenever you just use like a general amount of heat, all you do is draw the triangle above the arrow. You can use specific chemicals. So like manganese dioxide is the one up here. Or sometimes you can change the pressure, like the atmospheric pressure. And again, you just communicate that. Okay. For us, the big one is heat. So in your notes, put down what this little triangle means.